Oh, it's so great to be here. It's so great to see you all. In case there's some noise outside, I just want to acknowledge, you know that there's a strike going on out there. And I just want to state that I'm in solidarity with the grad students and the postdocs. Everything that we do is carried on the back of them and their work, okay? So just in case we get disrupted, I'm not going to get annoyed about it, all right? So I am charged with talking about some science, but also representing our program, right? And so I gave a title, and the title is important, right? Because it is the landscape of multi-phase flows, okay? And so no words are chosen by accident. There are two things that I love that are rich with metaphor. One is surfing, and one is landscapes. Both of them are used often as a kind of metaphor. You can crowd surf, you can surf the internet, but if you just say surfing with no modifier, there's only one thing that it means, right? The best sport there is. The other thing is landscape, right? So you can talk about an energy landscape, you can talk about a fitness landscape. We use this term for a lot of different things. But I always say, especially when I'm talking to physicists, when I say landscape, I mean straight up, you know, you look at your camera and it says you want it in portrait mode or landscape mode. It has a mountain on it, right? That's what I mean, okay? I am a geoscientist, I think pretty literally, and landscape here means a physical landscape. And so we're going to be talking about landscapes, like landscapes outside, and we're going to be talking about some of the physical processes that form them and the challenges in particular that we've been facing in trying to understand them. So the other part then that I need to talk about here is the multi-phase part. So I have spoken to a few white dwarfers, and I said multi-phase, and a few people immediately said, oh, okay, you know, like phase transitions, right? And so they're thinking like the, you know, a pressure temperature diagram, and you have something like this, and you say, right, I've got solid, liquid, and gas, that kind of thing, right? So this is phase transitions in a traditional sense. We are going to talk about phase transitions today. So that's one aspect of multi-phase that if you were going there when you thought that, indeed you're correct. However, that's not the primary thing that we mean in our program when we say multi-phase. So when we say multi-phase, so this is maybe one definition of multi-phase is phase transitions of a material we might be interested in, like water. But the other thing that we're talking about when we talk about multi-phase is mixtures of things that are solids, liquids, and gases, right? And so that's the thing that we've been preoccupied with during our program. And so to give you an example, let's say that we have like a flowing river right here. We have some flow velocity profile of the liquid moving downhill, but the river is carrying particles within it. Sand, gravel, mud, boulders, something like that, right? And so this is one example of a multi-phase flow, right? And you can imagine when you look at a flow like this, that you can start thinking about, okay, maybe these particles are going to bang into each other. These particles are being carried by the flow, so there's some drag and lift force on them. Maybe those interactions can be homogenized in some way with some mean field model where we can treat it all as some single phase that's mixed, and that's okay for some problems. But maybe something happens. Maybe there's some special interaction between the grains or between the fluid that you can't average or homogenize away, and that's going to present some special challenges, so I want to focus on some of those problems. Another example of a multi-phase problem is something like a cloud, right? So you have here a turbulent gas that's swirling around in here, but inside of it is a bunch of liquid droplets. And the question of concern is how those droplets are going to interact with each other and coalesce to eventually make rain, and the challenges with that, right? And so now I'm going to tell you something about why this is the very worst thing to study if you're interested in physics, okay? It's the very worst thing, except I'm trying to implore people to do more of it. Okay, so first of all, yes, we can't avoid it, right? The flows that we look at outside, I was just staring at the waves breaking on the beach, kicking up these plumes of sediment, right? And you stare at that situation and you see these complicated vortices and all these billowing clouds of sediment, and you realize it's a turbulent flow, and we know that mixing in turbulent flows is hard. We know that turbulence is an unsolved problem in classical physics. There are parameterizations and different treatments we can do under different conditions, but it's not really a general solution that we can use to describe turbulence at the scales that we're interested in for very large flows, okay? So that's one problem. And the other problem is the Earth's surface. And I'll just be honest and say this material properties of Earth's surface is one of my passion projects. We live on a fragile planet. Fragile in the sense that we need to protect the environment and all that, but fragile also in the sense that the landscape that we walk on is metastable, okay? The soil underneath us appears to be solid. You rain on it a little bit, you shake it a little bit, something like that, and that soil, which is apparently solid, suddenly becomes a fluid, loses its rigidity and flows, okay? And so the point I want to make there then is that we live, we operate, we build on, we die on a granular landscape that is excited by a turbulent flow. So turbulence is hard, granular materials are hard, the interactions between them is crazy hard, and you wouldn't ever want to get anywhere near this except that this is the world that we live in, right? And so we're confronted with applications of these problems all the time, okay? And so this is the reason why we're going to try to link these two pieces together, right? And that's some of the things that we're trying to do in this program, right? So, just to be clear, I'm not going to give any kind of treatise on turbulence, but just in case you haven't heard about it or you haven't thought about it in a while, you know, I like the classic drawing of like, you know, a flame on a candle and the smoke comes up and then you see it start to billow, right, and become turbulent. And the important thing for us about turbulence in thinking about these flows is that if you are worried about mixing in a flow that is not turbulent, that is laminar, and we'll get to that definition in a second, then the mixing is essentially associated with Brownian motion, right, or with thermal kicks from the fluid. And so if you're worried about a particle in a laminar flow, it can be pushed by drag, but it's not going to fluctuate or do anything that crazy, right? But if we're dealing with turbulence, we now have the situation where mixing is not occurring at the molecular scale. Mixing is occurring at the scales of eddies and vortices, right? If we stick a fan in here and we watch the fluid motions induced by the fan, we'll see eddies of all sizes up to the size of the room, okay? And so mixing is accomplished by eddies that have a power law distribution of scales all the way up to some finite size limit, which may be the size of this room or some other boundary condition, okay? And so now what I want to make a point of is there are some cases where we can kind of average these things together, but nature confronts us with a series of patterns that tell us that mixing or averaging these kind of behaviors away isn't going to describe some of the problems, right? So one example that I could give is basically when you see patterns in a landscape. So this example that I might have here, that I'm drawing here, let's just say an example of mud cracks, right? So you have some initial particles suspended in a fluid and you let it dry, right? The material contracts, it cracks, right? And so you look at mud cracks, for example, and you see this localized failure happening in these cracks, and you understand that there's localized failure that's happening in a material as the liquid is undergoing evaporation. So this transient forcing of evaporation is causing stresses that make this material break. If you want to think about how that's complicated is, imagine now you want to re-wet this material and homogenize it again. It turns out you have to put a heck of a lot more energy back into these mud cracks if you want to homogenize them and mix them and make them a suspension of particles and fluid again. Because when you evaporate and you actually zoom in close, you evaporate and evaporation pushes these particles together by little capillary bridges. You can push these particles so close together that they enter the van der Waals well and they bond. And then you now have to get rid of that too, right? And so it's just to make the point that if you start thinking about the Earth's surface, there's localized failure and transient forcing that create new, fairly stable states, right? And so nature is constantly manufacturing new materials by fluid-particle interactions on the surface of the Earth all the time, right? So another example of instabilities is essentially all landscapes, right? So if you think about a nice meandering river that you see, I have it coming into the picture, and so imagine you're looking in plan form from above, but now I'm trying to draw a cross-section of the channel here. So you have fluid flow. When water runs over a surface in an initially thin sheet, you might imagine that it could just run like that forever, but no, it always spontaneously channelizes and makes a river, right? And so when you make a river, it's made by a multiphase material. It's water picking up particles from the bed and eroding them and transporting them. And one thing about this is that the flow makes its own container, right? So in the beginning, flow is running over a smooth surface, there's some initial instability, but you start having a complex interaction between the flow and its boundary. If there's differences in stress, then you cause erosion that change the shape of the channel until it satisfies the constraint that it's in equilibrium and maybe not eroding anywhere. That's a multi-phase interaction that creates its own boundary, right? Another example that we've been thinking about and talking about, it's one of my favorites also, is sand dunes. So if you're not used to looking at sand dunes, like in the desert, we're looking down from above. There's these classic bar-can-shaped dunes, as we call them. They kind of look like boomerangs. And so these things form when a flow is going from left to right, a steady flow. And what happens, again, if you're looking from the side, is that if you have a turbulent flow moving over a flat granular sheet, in the beginning, what you might see is just a dilute gas of particles hopping along as they're excited by the flow, and everything's flat and stable. But there's instabilities that happen, right? And of course, this surface becomes wavy, and the surface eventually grows. We're now looking at a cross-section here into a dune. And what I want to point out is that in the beginning, the initial waviness of the surface is kind of it's not a trivial, but it's a simple linear instability that we can understand from linearizing the equations of motion, like the Navier-Stokes equation coupled to transport. However, once this bump grows and it starts perturbing the flow, now the topography and the flow are talking to each other. And the way that the airflow is talking to this lump of sand is through the movement of sand grains that are bouncing along the surface, right? And so there's this non-trivial coupling in this multi-phase flow that gives rise to these kind of patterns. A pattern that we might care about, that I want to point out as a multi-phase flow and an instability, is something like landslides that can create debris flows, right? So now we're looking at a mountain kind of in perspective view, and an earthquake happens, or it rains a lot, and suddenly you have a slump of material that fails and flows and excavates a valley. That material flows out and spreads and deposits here, right? And so this is an example of the soil being apparently solid. You add a little bit of water to it, and something changes the frictional interaction of the particles in this landslide, and it suddenly flows, right? And this is another example. It creates a scar on the landscape, and this is a flow that sets its own boundary, and it comes out here and deposits and freezes. And so understanding all of the interactions of the fluids and particles are necessary to understand when this landscape will fail, how it will flow, and how far it will go, right? And of course, another example, the last example I'll give you of a pattern, which I've already drawn up there before, is the cloud, right? That's another key piece of our landscape portrait, right? We have the mountain, we have the river, we have the cloud, right? And at least from my perspective, it's kind of non-trivial that these boundaries appear as sharp as they do, right? And that these clouds are kind of organisms where they grow and they shrink, but they maintain some kind of persistence, right? And so this is a pattern that's created by an interaction of aerosols and particles and air that is blowing, and it's something that we want to understand. So before I get into some details, I just want to lay out what I think some of the challenges are, like the hard bits that that you should have in your mind about, that even if you don't work on these kind of problems, you might imagine what makes these kind of problems challenging, okay? So the first thing that makes these things challenging, which is probably obvious from the pictures that I've drawn, but it's the multi-scale nature of these problems. In particular, what I like to say from grain to landscape. Grain can mean like a grain, like a sand grain, but you could also consider any particle like an aerosol or droplet in a cloud as a grain, right? So there are literally direct connections between the interactions of particles at the grain scale and landscape scale patterns that form at the scale of kilometers, hundreds, even thousands of kilometers, okay? And so we know the deal with multi-scale problems. There's kind of no magic formula to doing it, right? You look to understand something fundamental at the small scale interactions. You look for some averaging or homogenization scheme or some intermediate asymptotics so that you can jump to the next scale where there might be some emergent nonlinearity and so on. But in a lot of these problems, the separation of those scales that might allow you to do that problem is something we're wrestling with, something we haven't figured out how to do, right? The other thing then that I want to point out is related to these patterns, and it's the sometimes extremely localized nature of the dynamics that we're interested in. And so again, pointing at this landslide example, we might have a deep column of soil, tens of meters deep, and it rains on it. So the soil everywhere is getting progressively wetter, obviously not uniformly everywhere with depth. But if we're looking at this from the side, what happens is somewhere inside of this granular material, it fails. All of the shear gets localized in a very, very narrow region, right? And all of the action happens across there. Now, of course, once this thing fails, the shearing nature of this granular blob above can actually shake itself apart. And so this block slides along a localized region as a solid, but then it can fail and it can shear itself apart and become a fluid. Okay? So this localized dynamics is one of the things that really frustrates averaging or homogenization or coarse graining, right? And we have this kind of localized dynamics in all of these sorts of problems. There are interfaces, and the interfaces can be very sharp. They can be interfaces in structure, they can be interfaces in dynamics, and oftentimes they're interfaces in both, right? And the last part is that, which I mentioned earlier, that these geophysical flows make their own boundary, right? And so when you think about the debris flows that happen in Montecito, you see these things ripping down the fans, you see them spreading out, and so you might want to think about what's going on inside of them in terms of the fluid-particle interactions, but you also have this very sharp boundary going on, and that boundary spreading in space and in time. And so a lot of the problems that we care about, and especially that we're worried about, if you want to connect the physics to something like hazards, involve these highly transient situations with flows that make their own boundaries and that are evolving in space and in time. And that's a wicked hard problem to deal with. And so there are a lot of brute force simulations that happen, but one of the things about our workshop, it's not that we are averse to brute force simulations. There are many of us that do that. However, we're also interested in trying to figure out what the upstream, like zeroth order physics questions are that might be frustrating our ability to make these simulations be predictive, okay? So I feel like I should motivate a little bit about why we care. I mean, maybe by the set of examples that I brought up, it might be a little bit obvious why we care. But I want to be explicit about that. So first of all, there's a lot of interest here in this workshop on cloud physics, and I'm going to get into what has kind of emerged as one of the central questions there. Clouds are pretty important, okay? So they're important for the radiative balance of the planet. And it's one of the big uncertainties in terms of climate change. The radiative balance of the planet from clouds, is it going to be positive or negative, right? And this is one of the big challenges. The other thing about clouds is, of course, it matters a lot how much it rains and where it rains, right? How that rain and the intensity with which that rain is delivered. If we go back to the Montecito debris flow example that happened in 2018. So I'm from the East Coast. Would you get 3/4 of an inch or a few centimeters of rain? It's not a lot of rain from where I come from, but there was that much rain in about 10 minutes. And so if you take that much rainfall in 10 minutes on a dry soil, it rains so hard that you can saturate the soil because you're raining faster than it has the ability to percolate or infiltrate into the ground. And so if you rain really hard, you take the same amount of water and you deliver it over 10 minutes instead of 1 hour. That could be the difference between catastrophic failure and just the water gradually being absorbed into the ground and being slowly released into a river as groundwater, right? So the timescales really matter. So we know that climate change is driving more extreme events, more extreme heat waves, but also more extreme rainfall events, rainfall intensity. We know that that is driving things like wildfires, and we know that those things together are causing things like this to become more common. So more burning of plants that grow on mountains and hold soil together, and more intense rain that saturates the soil and makes it fail, and you get more debris flows and landslides. And this is beyond debate at this point. We now know that wildfire, landslide, wildfire debris flows are more and more common in the West, right? And so the other reason that we care, I would argue, is that we live here, and here, and here, and here, right? We live in these places. We actually harvest these materials as resources for building, right? And so there's a sustainable development aspect, which is the way in which we can understand these kinds of flows so that they're not at least significant hazards for us, but also ways in which we might harness these flows for meeting human needs, whether they're for energy or whether they're for sustainable building materials that make use of leveraging our understanding of the mechanical properties of these native materials, right? Which would be soils. So I'm getting to the main figure for the talk. Are you all ready for it? Are we there? Okay, good. Because I'm going to use this figure for the rest of the time. I don't want to make it too dramatic because my drawing's not very good, but my timing is good. So, okay, so I'm now want to try to show you the landscape of multi-phase flows, or at least the way that I think about it, okay? So, for simplicity, I'm going to consider particles and a fluid. The particles, you can think of these in the demos I'm going to show you in a minute. You can think of these as sand and water, if you like, okay? They don't need to be anything exotic at all, right? One thing about our program, we're working with literally very down-to-earth materials, right? We're interested about things like water and sand, okay? So, I'm going to call the y-axis is going to be volume fraction. And the way to think about this is if I've got, say, a cubic meter of volume, how much of that volume is filled up with particles, right? Or solid, and how much of that volume is filled up with whatever fluid they're in. It can be water, it can be air, it can be oil, right? Who cares? And so volume fraction of 0 would be a volume that has no solids in it at all, right? And a volume fraction of 1 would be a completely solid material, no voids, which none of the granular materials are, right? But something more like this table, right? And so that's what we're going to be talking about on the y-axis. On the x-axis, this is a little more tricky to do conceptually, but I'm going to call this flowability, okay? How easily something flows. So flowability is increasing this way. If you want to think about that as an inverse viscosity, that's fine. If you want to think about it as just some velocity, speed at which this stuff can flow, that's fine. If you're inclined, we like to think of it as a shear rate, a rate of deformation within the material, and often we non-dimensionalize it. But this is some measure of flowability, okay? And I want to make the point then that if we have a granular material, let me just make a line here, a phi about 0.6. So if you have a granular material, soil, sand, something like this, where the particles are really jam-packed together, there's a pretty simple premise that I think everybody can get, which is that if the particles are really crowded together and they're not able to move around each other, then that material can be fairly rigid, right? And if you were thinking in normal phases of matter, you would call that a solid. And in a granular material, we tend to call that jammed. And the reason we use the term jammed is it refers specifically to the volume exclusion effect. It's the idea that the reason that these grains can't move past each other is that there are constraints on the motion that are geometric. Even if these particles had no internal friction, just crowding them enough together that they can't move around each other makes them jammed, okay? And so if you have a jammed material, it doesn't flow. At least it doesn't flow very much. We'll get into, it does do a little bit of flow, right? But if you have this jammed material and you want to make it flow, so you apply some energy to it, you apply some stress to it, you push on it. If you want to make it flow, what you need to do is dilate it. These grains you need to expand the volume a little bit so that these grains have a little bit of room to move around each other, okay? And so what that means is that if you want to take this material and make it more flowable, what you have to do is slightly decrease the volume fraction, right? So just going from the jam state and just loosening up a little bit, you've loosened the constraints on motion that come from the grains being crowded together, and the material can flow. And you can draw a curve that goes down like this, that basically says, if I want this mixture of fluid and particles to flow more and more, I need to have fewer and fewer particles. So one way to think about it is if I had a dense suspension of particles in a liquid and I started taking particles out, that the viscosity would go down and down and it would flow more and more. Or alternatively, if I have grains in a fluid and I want them to flow more and more, if I shear them or push on them harder and harder, that the grains will expand and the volume fraction will go down, right? Okay. And so as we move along this axis, we're moving from a situation where materials are jammed, and then there's this transition where the constraints of motion are reduced. And so this is like an unjamming transition. So the grains are able to start sliding around each other, and you'll see a fairly rapid unraveling of the material. You'll see it begin to flow, okay? And so as you move along this axis, the material is flowing more and more. And so if you want to think of this in terms of some kind of phase diagram, now very loosely and fuzzy phase diagram, okay? Not like a hard definition of phase diagram like the water one, but it's that this thing here is a solid. There's a regime in here now where the particles in the fluid mixed together are behaving as what we would call a dense suspension, but is effectively a liquid, okay? And what does that mean? So now in this regime, you have some intermediate density in here. So now the particles maybe aren't touching frictionally anymore. However, the particles can still talk to each other through the fluid, right? So the fact of the matter is that these particles are crowded together. Each particle moving in the fluid is leaving some hydrodynamic wake behind it because fluid mechanics is hard, because you know, these flows I'll talk about in a second where they can be in terms of Stokes and Reynolds number space, but there's this regime where it's all friction, this regime where grains are interacting but predominantly hydrodynamically, and then there's a regime over here that we call a granular gas where the particles are suspended in a fluid but they're so far apart from each other that there's not really any interaction at all. This case is pretty simple in terms of an understanding how the material flows behavior, but there are some other non-trivial problems with this case, because the question is, do particles in a real shear flow out in nature ever stay like this, really well dispersed, even when they're dilute? And it turns out, no, they don't. That even a nice dilute suspension, the turbulent flows can collect those things together at a concentration that are surprising. So there's a couple important things that we need to define here then. So first of all, one way that you can think about this, increasing energy, we can think of it through an increasing Reynolds number for the fluid. So we're going to define a Reynolds number for the fluid. This is a very simple bulk definition of the Reynolds number for the fluid, which is just going to allow me to tell you about the importance of turbulence, okay? So the Reynolds number that we're going to talk about here, we just take the bulk density of the fluid, right? We take some representative velocity scale of the fluid. We take some representative length scale of the fluid, and you divide it by the viscosity. Okay, so this is a measure of like the inertia of the flow compared to the viscosity of the flow. And if you think about mapping geophysical flows onto this diagram, which I'm going to do in a minute, these ones with effectively really high viscosities in these really dense suspensions, if you homogenize over it, you consider it one phase of flow. It's a very sluggish, low Reynolds number flow, right? And if you go all the way out here for the kinds of flows that we think of that are very dilute, so aerosol droplets in clouds or dust, you know, dust being kicked up when the wind is blowing on a street or something like that, these are situations where the Reynolds numbers of the flow are really high, where turbulence is pretty relevant, right? And so you can think of this axis also as an axis of the flow becoming progressively more turbulent, right? And so if you want to get an idea about why that might matter, I think of just the simple case of a flow around an obstacle, right? So if you have Reynolds number, say, small, less than 1, if you have a flow coming and it sees an obstacle and you follow the streamline, it goes right around the streamline, right? Goes back to the other side like this. Everything's fine, right? This is like you driving up to a traffic circle and you're driving nice and slow and you just follow the traffic circle around and you come to the other side and you continue, right? The other situation where the Reynolds number is large, let's just say arbitrarily large, bigger than, say, 10 to the 3. People will argue about what fully developed turbulence is in terms of Reynolds number. It's not totally well defined. But now you're in the situation where perturbations in the flow grow. Any perturbation to the flow is going to grow. And so if you're looking at flow around an obstacle like this, you follow a streamline and it hits a perturbation and all of a sudden the streamlines get all wiggly and you start generating huge amount of vortices, right? And so this is what's happening in the high Reynolds number regime. And as usual, there's a transition. And it turns out that in the transitional regime, lots of non-trivial, interesting things happen, right? So the flow hits this obstacle, and at first it appears like it might recover, but then it starts developing this vortex street, which is growing like this, and what you're watching is the development of turbulence from a perturbation, okay? So if you then think about these kind of flows, you're in the laminar situation here. Flow's not doing anything that complicated, and over here you're in the turbulent situation. Now the other thing you have to worry about is the particles that are in the flow, okay? So the particles that are in the flow, we're going to define a dimensionless number that says something important about their properties, and we're going to call it the Stokes number. Now there's lots of Stokes numbers in the world, like a lot of the dimensionless numbers in any community. People use a dimensionless number under different contexts and they give it the same name, but it has slightly different variables. So for here, I'm just going to define a Stokes number in a way that really, sorry for the specialists, is more like a particle Reynolds number, but it's the density of the particle times the speed of the particle times the diameter of the particle over the viscosity of the carrier flow. And so this can either be thought of as inertia of a particle compared to viscosity, or of the relative time scale of the particle moving compared to the time it takes to push fluid out of the way. So what do I mean by that? So we can think of a situation where the Stokes number is much less than 1. So now let's imagine a flow. So there's some fluid, some liquid that is flowing and it hits a wall, right? And it spreads out. Now imagine a particle that is in that flow. If the inertia of the particle is very, very small, this particle acts like a tracer, right? So this particle follows the streamline of the flow, and whatever the flow is doing, the particle's doing, right? Like this. Of course, there's another limit over here where the Stokes number is really large. And now you're in bowling ball territory, right? So the particle is moving along, and the flow turns, and the ball just goes careening straight into the wall, right? When a Stokes number is around 1, the behavior can get really non-trivial, right? Because now you have a situation, so the particle is mostly following the streamlines as long as there's no rapid changes in direction or accelerations or decelerations, right? But the particle has some inertia, it's not negligible, and so the particle might start to follow, but then do something like this, and then when it gets to the wall, is it going to go up, is it going to go down, right? It's kind of hard to predict. And so again, there are these limits, right, of different importance, but the transitions are really hard. In the transitions, the coupling between the particle and the fluid is kind of maximized, okay? And that can make things really tricky, and unexpected behaviors can happen. All right. So now I'm going to map this to a landscape. And so it's important that I keep these transitions here. Okay, and so what do I mean by a landscape? I mean like a literal landscape. So we're going to start in the mountains, and we're going to take a journey from the top of the mountain to the sea. Okay? All right, so I'm just going to draw some profile like this. And then here we are. We reach the ocean. Okay? So this is a tall mountain. We're following down the flank of the mountain. This is a river channel that's in the mountain. We're looking in profile here. Okay, and so this unjamming transition is the regime where landslides happen. This happens in very steep slopes in mountains where the soil is close to the angle of repose, and some slight perturbation or some slight addition, some change in volume fraction and some slight addition of fluid can cause it to fail. Okay? So if you want to know what's associated with this kind of transition, be thinking about landslides, discrete slumps of soil that moves down. I don't want to get too into semantics, but if you start adding more water to this, you now have what happened in Montecito, what we call debris flows, okay? And so debris flows are flows of very high concentration. However, they're very fluid. They're behaving as a viscous liquid. They have some interesting behaviors to them. And one aspect that we're going to get to in a little bit is that it is a multi-phase flow where it's particles and a liquid. And the other thing that happens is there are multiple kinds of particles that are mixed together. And so in this kind of flow, for example, if it's water and small particles like clay and sand and big particles like boulders, then they will also separate into a flow that has big boulders at the front that act like a battering ram and an ocean of mud behind it, okay? And so these kinds of things are hanging out here right in the middle, right? These are in the liquid stage, but still pretty dense. And if you want to get an idea about where we sit, okay, these ones are in that transitional regime, okay, roughly, okay? They bracket it with a couple orders of magnitude on either side, but these kinds of flows, these debris flows, are transitional in terms of laminar to turbulent and are also transitional in terms of Stokes number, right? As we go further down, the concentration of particles is getting smaller, the amount of fluid is getting bigger, and so you can think of this now here as a river, okay? So the river now is mostly clear water. That clear water is shearing up against a granular bed at the bottom, okay? But that river is also carrying a dilute but non-negligible amount of particles in it, mud, silt, sand, other things that are getting delivered to the ocean, okay? And as we follow this all the way down to the sea, right? So now what happens when this river, laden with particles, hits the ocean? We have another geophysical problem because now the ocean is salty, right? And so it's more dense than the fresh water that's coming in. On the other hand, this fresh water is carrying with it particles, and those particles are dense enough that they settle. And so on the one hand, so you have this stratified flow where the fluid wants to do one thing, and the particles want to fall down and do another thing. And it turns out that that interaction of the particles decoupling from this fluid and falling through here produces some non-trivial mixing behavior also. Okay, and so this is meant to be then, for the particular case of soil and water, a linkage from the multi-phase flow kinds of problems to the literal landscapes that these flows live within, right? To give you some idea of what we're facing. So, okay, so we have a demo. Ben, can you come help? Okay, so I want to give you an intuition about why, first of all, just even dry, mundane, granular materials are actually pathological, right? So Ben has an experiment that I want you to tell them about.
Yeah, so this is what I'm doing for my PhD.
Okay, here, just take mine. No? Okay. All right.
Thank you. Can you hear me? Okay, so this is just a hopper filled with plastic particles, basically. And it looks pretty boring at the moment, but these particles are what we call photoelastic. So when a stress is applied to them, they rotate the polarization of light. So these are two cross-polarizing filters. And when we turn on the light...
Yeah, which one? Is it this one? Okay. Here, let's see.
Suspense is building. Yeah, you can see the distribution of forces inside the material, and it's not trivial at all. There's some particles that don't have any force through them, and chains that are carrying all the force. So this experiment is looking at why things clog. So when I remove the stopper at the bottom, they'll hopefully flow and then stop flowing. And we want to be able to use the distribution of forces to see if we can explain that. So I'll run it now.
Yeah.
pace of the flow that supports the weight of all the other particles.
Yeah, and so the two things then that you notice about this, first of all, the stress is distributed in a highly non-uniform and localized manner, right? And so you can get a kind of spooky action at a distance, right? Because you can push on a particle over here, and then it's going to transmit that stress through a force chain all the way to some other particle over here. The other thing you notice is that that arch at the bottom, that one little bit of local structure, is a highly localized collection of material that is determining whether or not the bulk flows or not. And so you can imagine that if you're trying to predict a state of flow or not flow in a material like this, which is just a granular material, right? The only difference is that it allows us to see the forces. You can start to understand why that's a hard problem, right? Everybody get it? Okay. Awesome. Thank you, Ben. Okay. So, cool. So there's this highly localized behavior in the arching, and there are also non-continuum effects, right? That's a highly discrete, that all the stuff that you're seeing there is due to the highly discrete nature of the problem. It doesn't mean that there's no way for us to go to some continuum limit, but there are challenges in doing so, okay? And so there's now a simpler demo that I'm going to do for you that I don't need the camera for. So I'm going to go from, now here's some sand, but within the sand right here is all the stuff that's going on in there, right? We just can't see the forces, right? So we know the sand is innocuous enough. It's sitting here like a solid, behaving pretty well. But we know that if we take this thing and we tilt it, right, that it flows like a fluid. So I want to make the point that even dry sand like this undergoes phase transitions, right? Now, wait, that's not the water that I wanted. This is the water that I wanted. This sand, by the way, is just from the beach over there. It's nothing special. You can do these experiments yourself. So if you cook, then you understand the non-trivial behavior of granular material as you add liquid to it, right? And so if I take this granular material and I just add a little bit of water, right? So I just splash the water around. It's dry, and I put a droplet on, and there's capillarity that sucks that water in, and it makes clumps, right? And so right now I've added a little water, and the granular material is still sliding around. It just has some clumps in it, right? So that's fine. That's not that interesting. Let's add a little more water to it, right? And so now I've got this material. I'm sloshing around. And if you do this with flour cooking, right, you understand that you add more water and it clumps more. And if you keep adding water, it's going to turn into a kind of paste, right? And so what's happening is, as you're adding water, you're building little capillary bridges of water that are pulling the grains together. And so this is a three-phase problem. And even though it's trivial to do this kind of experiment and to change the flow behavior of this material, actually understanding what's going on in here is very challenging, right? And so now you can add sufficient water to it, and it starts flowing together like a single-phase material. But if you leave it sit there, it's going to phase separate. These are heavy sand particles. So now if you want to make a suspension of this stuff, so you want to keep it flowing and you want to stop these particles from settling, you realize you have to add a lot of energy, right? And so we're thinking about flows of heavy particles, right, keeping in suspension instead of just falling out and depositing. You start to get a sense of how much, let me rinse my hand off, how much energy you need to do that, okay? And so I'm going to finish with a few challenges, okay, right now, that we're wrestling with as part of our program, right? And they're related to, first of all, that unjamming part over there, okay? And so I can draw for you another kind of phase diagram, right? And another kind of phase diagram that I'll explain in a second. It looks something like this, okay? So I mentioned that if I have a granular material mixed in a fluid at low enough volume fraction that it can flow, and if it's at a high enough volume fraction that it's jammed. But volume fraction is not the only thing that matters, of course, right? And so I can have, if a material is dilute enough, it will flow, because the grains will never touch. And if the grains are crowded together enough, it will never flow, no matter how hard I push it. But there's a regime in the middle where a mixture of particles and fluid might flow or it might not flow, depending on the stress that's applied to it, okay? And so understanding this in-between regime here is a frontier problem, okay? And so, first of all, the fact that we have this kind of phase diagram, we have it in very idealized systems, and it's hard to generalize, despite the fact that we know that a granular material might flow or not flow for a given volume fraction, depending on the stress. If you want to go to the problem of saying, now I'm out in nature and I just rain on dirt, and I want to know the stress state and the volume fraction state and whether or not it's going to flow or not. You can't go from that phase diagram to this, okay? So we have highly idealized laboratory experiments where we can control everything perfectly, and we can come up with these kind of phase diagrams, but the moment that the boundary conditions change, our ability to predict goes away, right? And so that's one major challenge, right? So another challenge then that I want to talk about is related to these dense flows right here, right? So I'll call that one number 1, and I'll call this one number 2. And so I mentioned this earlier with these debris flows or these dense flows. And so first thing is that we're worried about the separation or the segregation of these grains. So we have a highly heterogeneous mixture of dirt, mud, boulders, water that's flowing down, trucking down a channel 10 meters a second, and what we almost always see is that there's big boulders in front and this ocean of mud behind. Now, we know if this were even a dry granular material and it was a mixture of big grains and small grains, and you were to shake it or shear it or make it flow, we know that if we started with a heterogeneous mixture of big particles and small particles and we had them in a shear flow, that what would happen is that that flow would segregate. Because what happens is, people call this the Brazil nut effect. You might have heard of it, like you have a jar of mixed nuts and the big Brazil nuts always end up on top, right? And the situation, there's some deeper physics behind it, but the short of it is kind of a ratcheting effect. That if these grains are being jumbled around during flow, if a big grain happens to pop up, a small grain falls underneath of it and the big grain can't go back down. And so if you shear it and jumble it up enough, what will happen through time is that the big grains will float to the top. And in a flow like this, where the fastest velocity is at the surface and there's a no-slip condition at the bottom, what's going to happen is that grains that float to the top will get delivered to the front. So if you have a dry granular material, it will phase separate and the big particles will go up and they'll go to the front. However, you could also think of this situation in an opposite limit that simply says, let's say that the mud and the particles are behaving as one carrier fluid. From the perspective of these big boulders, all that sand and mud mixed with water is just a viscous fluid. If you do an experiment where you just take like viscous oil and particles mixed together and flow them down a steep plane, what will happen is you get a phase separation. Because the coarse particles are experiencing both the drag from the fluid pushing against them and their own gravity pulling them down. And so what will happen is you separate into particles in front of the fluid. And so when we're thinking about this problem like these debris flows, we don't even know whether or not these deadly phalanx of boulders in the front of these flows is caused by a dry granular segregation phenomenon or a phase separation phenomenon, okay? And so that's a real challenge for us. One thing I want to bring up here is that another challenge is that the simplest kind of flow model basically says I've got this material and it's flowing over some bed, right? That's rigid. That's the easiest thing, right? Like the mud flow's moving over this floor. But of course, all these flows are moving over erodible granular materials, other soils that can be picked up. And as simple as it might sound to the outsider, whether we're thinking about this in terms of debris flows or in terms of other flows like rivers, one of the big breakthroughs in the last few years from our community is actually that this stuff underneath is not a static material, but actually itself is a granular flow. That granular flow underneath gets excited by the granular flow above because of the shear surface. And if you think of this, at the very least, the way in which this velocity profile decays into the substrate is a source of momentum, or a sink of momentum, right? And so you might think, at least, if I have to worry about whether this flow is losing or gaining momentum, and if it's going to pick up particles from the bed, I have to think about the way in which this crazy, hard to understand flow is moving over a bed and maybe picking up grains from that bed by shearing them from underneath, right? And so that's a challenge. And so the last thing So I'm about out of time, right? Okay. So the last thing that I want to talk about is the last demo. So Ram, can you come up? Yeah, okay. And so this is to go to the dilute regime over here, right? And so can you, oh wait, let me get you the mic. Can you tell them about your demo here? Here you go.
So in the clear, we have a bunch of salty water down here, and we have on top of it some dyed fresh water. It's lighter, floats on top. And then on the side here, we have a 3D printed piece, which is just gonna allow us to introduce a suspension in there, kill the vertical momentum, so it can be introduced in the middle of those two. And I'll just put in a couple of different suspensions, I think.
Yeah, so what we want you to be thinking of is now we're down here where the river comes into the ocean, and you have the stratified situation of dense salt water underneath, fresh water on top, but now you're going to have fresh water with particles coming in. And hopefully, we'll see some interesting or non-trivial behavior. Maybe we should move the light closer to the chute, because sometimes all the action is right by the chute, right? So. Did we see anything? A little bit, a little bit. Is that better? That's pretty good right there. I mean, well, relatively good. Just give it a lot.
Yeah.
I didn't really see anything. See, this is always the danger with demos, but
Well, I'm gonna put the bigger part.
yeah, let's put the bigger particles in. Just hit it with everything we got. The idea here, by the way, as you're watching, is that the particles, as they settle through this interface, there's a density contrast that sends the particles askew a little bit. And then the particles sediment, but they don't sediment one by one. They actually start collecting in streaky little bits. And so the settling of the particles as they collect in these streaky bits is actually faster than you would expect if the particle was settling on its own. And now you can see what happens when these particles hit the bottom, is that as these particles hit the bottom, they can even induce a density-driven current that flows away. Okay, and so there's two interesting aspects of this that are hard to understand. One is the way in which the particles in a turbulent flow actually collect together to fall faster than they would individually. And the other is that when these particles fall toward the bottom, they actually bring fluid with them. And when they hit the bottom, you end up with a self-formed mixture of particles and fluid that then itself flows as a dense flow down at the bottom. And the point that I want to make there is that this problem about the way in which particles in a turbulent flow get collected together at concentrations that are higher than you might naively expect, certainly higher than you would expect in a uniform flow, and the way in which the particles then interact when they're brought together is a problem for the sedimentation. It's a problem for understanding the interaction of particles that might stick together under that sedimentation, like clay particles. And it turns out to be a related problem in the way in which small droplets find each other in a cloud and actually coalesce together to make bigger particles that are finally big enough to fall as rain. So I'm going to stop there, and thank you for your attention.
Questions? Okay, Boris, hang on. The microphone.
So I was thinking about kind of when you have mud of fine grains which is saturated with water,
Yeah.
and you pat it and it becomes solid, so it's a non-Newtonian thing.
Yes.
Is that kind of one of your transition phases?
Yes. Yeah. And so, indeed. And so this was like this example right here, right? So you can have these particles at one volume fraction that are kind of flowing, but if you pat them or push on them, so you're applying a load to them, and you can actually squeeze the particles together into frictional contact. And so it is, so in terms of thinking of it in terms of rheology or flowability, we're drawing that line like there's a discontinuous transition, like it's flowing below and it's solid above. But actually, if you zoom in on it, you'll see that it's a rapid but continuous transition where like the viscosity is blowing up. And so indeed, thinking about the origins of non-Newtonian rheologies is one of the central aspects of this workshop. So there are some mixtures of particles and fluids where as you shear them or push on them, they get harder and harder to flow, right? And that typically happens with particles that are small enough that their surface charges matter and they're repulsive. So as you're pushing them, they can move around each other, but at some point you overcome the repulsion and they contact, and you get what we call shear thickening. But in other situations, if you have something sticky like mixtures of mud that kind of behave like a gel, or like toothpaste, where you can put it here and it seems like it's solid, but you push on it or squeeze on it and it starts to flow like toothpaste. So in that situation, particles in a fluid, just by changing the nature of the interaction of the particles, you can make it have the reverse behavior where it's shear thinning. And so the thing is that both of them happen out in nature depending on the particles. And it actually brings up a critical point that I wanted to talk about just for a second, which is that a lot of us come from a fluids background. So when we think about these multi-phase problems, we bring our fluid mechanics understanding to bear, and then we introduce the particles and their material properties as maybe an afterthought. But just the fact that you can go from shear thickening to shear thinning with the same size particles in the same fluid just by changing the interaction of the particles tells you that the big thing that we need to do is start paying a lot more attention to the materials themselves, which regulate the interactions of the particles. Yeah.
I have a more basic question. There has been a few accidents in Brazil in some mines.
Yeah. Yeah.
Let's call them accidents. And I was wondering if understand it is the, let's say, the type of material and the interaction of these different materials and the rain and everything that is actually being applied to help avoid these kinds of things.
Right. And so, in fact, we have talked about these catastrophic dam breaks in our workshop. And just for those that don't know, I mean, there are probably ones that I don't know, but there have been a few really catastrophic dam breaks where essentially what happens is that there's a river and the river gets dammed, so you have a pond, and you're mining on a mountain somewhere. And you're mining the mountain and you're trying to find the ore that you want, and then you basically make this tailings basin where you just chuck in all of the dirt and stuff that you don't want, right? So it's very common to build in mining, when you're mining up in the mountains, you build some dam to make a pond and then you just fill it with waste. And what you're talking about is a couple situations where essentially this dam, which is just made of earth, suddenly liquefies. And there are movies of this on the internet. It's catastrophic and terrifying. And it's just like a landslide. You have an earthen dam that was happily sitting there for a decade or more, and then it suddenly liquefies. It is exactly this transition. It is exactly this transition. We are not. Some people in the workshop, you can step up. You know, we're all on different ends from the like applied to basic aspect. But I would say that one of the things that we're focusing on right now is not anyone in the workshop directly predicting a failure like that, but looking upstream to saying, what is it? What are the limits to predictability in the models that we have that are related to the fundamental physics going on at the contact scale? So we're motivated by problems like that, but I would argue that our predictions are going to be highly empirical. They're not that grounded in fundamental physics, and that we're trying to make that connection.
Hi.
The force is just this hydrostatic, so there's a hydrostatic load right here, right? And so this pressure gradient from here to here is causing water to flow through the dam. And so often, if you don't want this dam to break, you'll say, okay, I'm going to install some drain right here. And what I'm going to try to do is to draw the water down into this drain and have it go here. But if you don't build a drain, which happens sometimes if you don't have money or you're in a hurry, or your drain actually gets clogged because it's pulling in water but also particles, then what happens is that the water flow starts to move through this porous medium, and it's just the fluid pressure from the water pushing from the back end that can cause the grains to lose frictional contact.
Hi. So this is just kind of a curiosity question.
Yeah.
But I'm wondering what sort of the unique properties of other types of flows are, like specifically pyroclastic flows.
Yeah.
And it's always been kind of interesting to me that those flow so incredibly fast.
Yes.
Compared to other things. Yeah.
This This is just proof. Sorry, my volcano friends, I just didn't get to it, right? Because I didn't want to. I had the volcano. It had its own slide. So we have volcano people here, and so indeed. So on the one hand, the pyroclastic flows are like just another fluid granular mixture. And what I mean by that, at the least, is that there's nothing in this framework of thinking about particles qualitatively in the nature of their interactions that is different for that kind of situation. However, there are some things, if the carrier fluid is a gas instead of a liquid, that can be different. One of the things that has been brought up in our workshop is that you start thinking about something like these Stokes numbers and things, is that some of the ways in which we model the pyroclastic flows come from the liquid particle models because people have been doing them for longer. But a bunch of things that have been brought up in this workshop is that in these pyroclastic flows, which for people that don't know, it's like a volcano explodes, it sends out shards of rock and super hot gas mixed together. They're actually typically, Garrett, correct me if I'm wrong, the most deadly common hazard from volcanoes is actually this crazy fast surging flow of hot rock and gas, okay? And one thing about it is that the Stokes number situation is different. The way that the particles settle out in these materials is different. And in fact, one of the things that's been brought up in our workshop, there is this problem about how dilute particles swirling around find each other and collect together and densify. And it appears that there are maybe qualitative differences in the way that that happens between particles and liquid, like in that river example, and like particles in a hot gas, like happens in the pyroclastic flow example. And we could guess that it's, we can start guessing based on our dimensionless numbers why those behaviors might be different. But we're at the point right now of recognizing those differences and recognizing our intuition that comes from the more commonly studied example of particles in liquid maybe is limited in how much it can extend to, creating and densifying the particles in these flows.
I wonder about, kind of the extreme motion, like say, the tectonic motion of continents, whether your science is applied to these circumstances.
So the question is about tectonic motion and whether or not the stuff that we're working on is connected to that. So there are very deep connections to this problem, the problem of landslides, and the problem associated with the strain localization, the fact that you have failure that gets localized along a slip surface instead of distributed uniformly in the material. And when you get down to the granular scale, the challenges that we're working on and modeling with this are just like the challenges and the problems of what's happening at the fault of an earthquake. Now, typically in an earthquake tectonic situation, the pressures are higher. So there are compressive pressures that make it such that this localized slip can be even more dramatic in an earthquake than it might be here. But there are very, very deep similarities. And a bunch of people in this workshop that work upstream, literally on the granular side, also have connections to the earthquake side. Yeah.
It seems to me that you deal with solids and gas, solids and liquid. What about the other, like gas and liquid? Most of our planets is this interface, and from the point of view of fluid dynamics, is a very complex problem. You don't care about that?
Well, I thought you were going to give me a softball question. Okay, so the gas, so of course a lot of this has to do just with the complexion of the group that is here. So if I zoom out more broadly, so are there communities that are really worried about mixing at the air-water interface? That's happening from the wind blowing or especially from waves breaking and things like that? Absolutely, right? There are lots and lots of people that are working on that problem of the mixture of, like air and water and things like that. I would just say that our group right now has concentrations of people. And if I were to break them up, the concentrations of people fall along, there's cloud physics, there's the sort of sediment transport, which is clearly the world that I'm in because I spent the most time on it. There's the volcano, like the volcano groups, and then a smattering of people that are interested, that sort of touch all those problems. And so it's just to say that that's a deeply important problem. It's just not one, we're really thinking about situations where, even in the cloud example, where it's a liquid and gas, it still is related to these other problems here in that there are particles, the aerosols or the droplets that are interacting with each other in a fluid. And so in order to have some common ground among the group, we're all thinking of particles in a fluid that way. And so that's just what steers us away from this problem. It's not because it's not important. It's just not represented that much in this group.
Thank you very much.